Okay, any questions from the last hour? This is, for me, the more fun part of the course. Very few equations now, at least for today. We're talking about applications. That's why we spend so much time doing the underlying spectroscopy. Usually the motivation for us is to have a laser technique that can be used to probe something that's somewhat unknown. It's some sort of combustor, some sort of propulsion system, something that's where we really don't know exactly what's inside, or we know closely what's inside, but we got to measure it directly to validate CFD. So how do you establish a technique to use in an unknown environment? You start by proving that it works in a known environment. So for us, the primary tool that I've been using a long, long time is a shock tube. So a shock tube is just a way to produce a very well-known controlled gas sample at temperature and pressures that are known. So you can test your ideas, make sure they're working fine before you take them to a system where you really aren't sure what's inside. So you have to calibrate, validate your system. So we use the shock tube as a controlled heater to produce controlled pressures and temperatures. We also use it to build a spectroscopic database using those same capabilities. But I'm also really interested in chemistry. So we use the shock tube as a step heater to trigger chemistry that we can study with lasers to contribute to reaction models that are used for combustion modeling. I'm going to present this in the spirit of someone to people who I think haven't used shock tubes. It'll be a bit redundant for people who know about shock tubes, but I'm going to pitch it at people who haven't used them themselves. These are just a couple of pictures that I have from Stanford, a couple of our different shock tube facilities. So I'm going to give you an introduction, and I use a couple of examples for how we could study the vibrational relaxation of gases or their ignition, and I'll talk about some advances in how we model these facilities. So they're nearly ideal, not perfectly ideal. They're nearly ideal, and we're always working to make them better and better and better. So in most cases, the shock tube is a long tube, typically about 100 diameters long, divided into two sections, a high-pressure driven section where we put gases to break this diaphragm, separating the lower pressure chamber, which is filled with our test gases. So it's the low-pressure section, also called the driven section, typically filled with test gas. We call that region 1. We call this region 4. And we're going to break this diaphragm, and we're going to watch the propagation of this wave down the tube, and we're going to measure its speed, and from that measured speed, we can calculate the conditions behind the shock wave. And then when the shock wave reflects from the end wall and leaves behind a sample here that's nearly stagnant, we'll be able to calculate those initial conditions too, and we're going to maybe propagate some laser light across there. So the concept is that high-pressure gas is like a piston. Remove this diaphragm, there's high pressure, acts like a piston, pushes, it forms a shock wave. Forms in about 10 diameters typically. So after about 10 diameters, you have a shock wave that's moving along. In an ideal world, the shock wave would move at a constant speed. It doesn't. It actually slows down a little bit. And we have to measure that and take it into account. The idea is that this test gas is instantaneously compressed because the shock wave itself is very thin, typically about 10 mean-free paths. So it's essentially a planar discontinuity in temperature, pressure, and density. Now down here is where we usually do our experiments. The experiments are either done behind the incident shock wave or the reflected shock wave. So the diaphragm breaks, not instantaneously, maybe a few milliseconds. A few diameters later, a wave is formed. It propagates. We call that the incident shock wave, and behind it now we call those conditions 2. High pressure gas expands, but it effectively acts like a piston. This essentially instantaneously compresses the test gas to some incident shock temperature. Then the shock wave reflects from this end wall, leaves behind a static sample, roughly doubling the temperature from what it was in 2. So there's region 1 is typically room temperature, or if we heat the shock tube, it might be 100 degrees centigrade. So we know temperature in region 1. We measure the shock speed. We can calculate region 2, and then we can calculate the region 5, which is assumed to be stagnant. So this is the place to be in most experiments, not always. So again, we can get essentially instantaneous heating. Essentially instantaneous, what does that mean? Microsecond or so or less. We have accurately known conditions, typically to within, if you're careful, to better than 1% in temperature and pressure. It's not exact. And we can generate kind of any condition we want. So right now we're doing experiments at about 8,000 degrees Kelvin for one particular project. But we've also gone as low as 600 degrees Kelvin, wide range of pressures from less than an atmosphere to up to 1,000 atmospheres. Typically, though, a few atmospheres is common. There's some history to the shock tubes, and is of interest to me. My understanding is that the first so-called shock tube was produced in France at around 1899. This guy was a railway engineer. I think they were having some sort of shockwave formation in their steam lines that were using associated with their locomotives, and they were experiencing pressure surges, and that led him to do some studies on shockwaves. So I believe the first shock tube was around 1900. Along about 1940 or so, there was a lot of interest in explosions, mine safety, aerodynamics. There were a lot of scientific things that started coming along, especially in the US, Canada, and Great Britain that I know about the time of that Second World War. That people were looking for ways to produce high pressure conditions or high speed flows, conditions that they might use to examine explosion behavior, propagation of shock waves in ducts, and so on. I believe that it was about 1950, and it might have been Caltech, but it might have also been someone in Canada who did what I'll call the first chemical kinetics experiment. Somebody realized that you could use this to produce a step change in temperature, which would trigger chemistry. You know, gases always progress towards equilibrium. But if you change the equilibrium point, it has to adjust, and you can measure that transition and call that a study of chemical kinetics. I believe it was about 1950, 52, 53, 54. Along about the late 50s and 60s, people became very interested in planetary reentry because the vehicles re-entering the atmosphere come in at high Mach number, enthalpies are high, the post-shock temperatures are high, and you have the problems of how do you thermally protect these structures. So a lot of interest in reentry. And I was involved in one project had to do with Jupiter entry. These are calculations of what would happen if you sent something to Jupiter and what would happen when it entered the atmosphere. It decided somehow that, well, you had to have Mach 25 or something like that in the atmosphere they believed to be around Jupiter. Well, how do you simulate? You can calculate it, I suppose, but how do you simulate in a laboratory? People became very interested in using shock tubes and shock tunnels to do high-speed aerodynamics. And of course, when you get to those conditions, these high temperatures, you have to care about the radiative loads, the time scales of the chemical reactions, a lot of things like that. Laser was invented about 1961 or so. To my knowledge, the first time the lasers were used in chemical studies in shock tubes. They were used quickly for studying laser Doppler anemometry and particle velocimetry sort of things. But to my knowledge, it was around 1970 that lasers were first used to try to measure a species in a shock tube. And as far as I know, it was done at NASA Ames. Finally, my group at Stanford. That's kind of the full history. So it's probably been about 50 years since, almost 50 years, we began to try to combine lasers with shock tubes. And of course, since then, what's happened is shock tubes have gotten somewhat better. The instrumentation has gotten a lot better. We don't have analog scopes anymore, for example. We don't use Polaroid recording of oscilloscope traces anymore. We have cameras, we have infrared detectors, we have a lot of improved instrumentation. And lasers have evolved so that now they're much more capable than they were in those early days. So this is a continuing story. It's not over yet. Now, what would you do these things? If I go to the every other year there's a shock tube symposium, and you go there. There's papers on astrophysics, nuclear explosions, chemistry, aerodynamics, heat transfer, a lot of subjects. Medical, they study volcano problems. They study shock waves interaction with kidney stones. So there's a lot of applications of shock waves that can be studied with a laboratory scale shock tube. The breadth of these activities continues to grow. I mostly have focused on spectroscopy and chemical kinetics and sometimes some aerodynamics. Okay, so I'm going to just show you some simple theory that would be, this is a book by Gaydon. It's probably a 50-year-old book on shock waves. Several books published in the 60s. So here comes the shock wave, essentially a planar shock wave. It's not exactly planar, it's slightly curved. And so here's region 1. We say P1, T1, rho 1. Here the velocity is 0. Here comes the shock wave, V sub s, leaving behind a moving sample of gas at conditions 2. And so you might say, well, how do we know what kind of a shock speed we're going to get? Well, if you do the ideal theory, which assumes that the shock wave is formed by the breakage of the diaphragm, separating therefore regions with P4 and P1, you can predict the Mach number from this complicated equation. And if you specify the specific heats in region 1 and the sound speed ratio between 1 and 4, and also gamma 4. So if you have the properties in region 4, which is the driver, and region 1, and if you assume a constant specific heat ratio, gamma, and if you assume no losses, the pressure ratio will give you the Mach number. So you can kind of bound what you're going to get. It's not perfect, but it's a guide, and it gives you some idea of what can be produced in the laboratory. The usual assumption behind reflected shock is that the velocity is 0. So the boundary condition here is the velocity is 0. And with that condition and with the incident speed, you can calculate the reflected shock speed that's necessary to stagnate the gas. So that's close to how it actually works. It's not exactly correct, but it's close. And from this, you can do some analysis to get a feeling for the conditions that you can generate. So for example, if gammas are 7/5, that would correspond to air, or gamma 5/3, which is appropriate for, say, argon. We do a lot of experiments with argon and helium because there's some benefits of having those inert gases. So for example, if we have gamma 5/3, and if we use a pressure ratio, I guess I'm not going to show you that. We use a pressure ratio of 10. I didn't do that right. If I had a Mach number of 2.9, I get a pressure ratio across that shock wave of 10. So pressure in 2 is 10 times higher. And then I get another factor 4. So I get factor 42 for P5 over P1 if I can produce Mach number of 2.87. And if I do this for temperature, take the product of these two numbers, so I'm about 6. I get a temperature rise of about 7. So in other words, I can quickly produce 2,000 degrees Kelvin with a Mach number that's only 2.87. Reflected shock speed tends to be about half of the instant shock speed. Okay, so these plots are probably going to be hard for you to follow, but they basically show, let's just look at this number here. If you do Mach 6, now I've got a pressure ratio, P5 over P1 of 260 or so. I've got a temperature ratio of I got about 9,000 degrees. Whoa. Of course, we don't yet know if we can produce Mach 6 easily, but in fact, everything scales kind of like the square of Mach number. So if you can work in this Mach number range, you can cover the temperature range in region 5 of, say, up to, say, 8,000. And maybe you can see these better than I can, but these are just plots versus Mach number. Now, I guess I left out, I'm not sure yet whether I'm going to show you the equation of what Mach number can be produced. So you might have this question, well, what Mach number could I produce? The people who wanted to study Jupiter entry wanted to know, well, can I do it? Can I produce Mach 25 into that Jupiter atmosphere? And it turns out that you can't quite do it with room temperature driver gas, P4 over P1. You have to heat the driver. So there are ways to, because there is the speed of sound ratio A4 over A1. So there's a way to get to extreme conditions by taking the extreme measures of heating the driver gas or detonating. So one kind of a driver is called a detonation driver. So you fill that driver with combustible gases and light it off, form a detonation wave, and so you instantaneously in the driver have, say, 3,000 degrees and 1,000 atmospheres. Now you can really push a shock wave. So that's the trick. But if you're going to work at combustion temperatures of 1,500 degrees Kelvin, you just need Mach 2. It's really pretty simple. So this is called an XT diagram. So this is the length of the shock tube here. This is the end wall, and this is our sensor location, 1 or 2 centimeters from the end wall. X equals 0 is where the diaphragm is. So what happens when, and this is time. What happens when you break the diaphragm? If you assume that it happens instantaneously, if you assume that, it will produce a shock wave that propagates at a constant speed until it hits the wall, separating region 1, region 2. Also, you can imagine that what propagates to the left is an expansion wave, which moves at the speed of sound into that driver gas, which eventually reflects as an expansion wave. Here's the test gas in here, separated by the driver gas. So the driver gas comes out like a piston and pushes this interface. There's the driver gas, the driven gas, separated by a constant pressure interface. Incident shock comes along, and so basically the amount of test gas continues to grow. Now the shock reflects and comes back, and it runs into this contact surface where there's a density difference. No pressure difference, but a density difference. That causes some sort of wave reflection process, which, if it propagates back to the end wall, marks the end of your test time. So that's the test time in a conventional operation. It might be 1 millisecond, it might be 5, it might be 10, it may be typically a few, depends on the temperature. So that's the traditional operation. If you do what's called tailoring and adjust the composition of this gas so that the density matches better at this condition, then this interface here between the driver gas and driven gas can be vertical, which corresponds to no pressure wave, and you can extend the test time. That's called driver gas tailoring. So the test time might be, I said here, 1 to 3 milliseconds, if it's limited by this effect. Here's the pressure versus time in an experiment. And if you don't have matching across this interface, this is region 2, this is region 3. One of the conditions for matching across that interface is that A2 equals A3, approximately. If you don't do that, then here's your test time, and then what happens is you see at this location right here, you see the pressure kind of undergoes a change, which you may not want. So this would be the nominal test time achievable. If you do the tailoring thing, you can keep this going longer. And that's a trick that we play when we need to, if we need more test time. If you're doing chemistry at 4,000 degrees Kelvin, you're done in a millisecond anyway. But if you want to do chemistry at 600 degrees, well, I need more time. We might try to get 4, 5, 10, 20 milliseconds. This is the case where you've tailored it. Now this interface moves vertically, meaning that mitigated that problem, the wave interaction problem. Now you can extend the test time. How long can you extend the test time? Well, eventually this rarefaction wave comes along, comes down. That might be 10 milliseconds, 15 milliseconds, depends on the geometry and the test gases. We have found a way to extend this even longer. This is our record. This is a record now. For T5 at 524 Kelvin and pure argon experiment, we were able to achieve about 105 milliseconds. So that's by far the longest time anyone's ever gotten. But we can only do this in a kind of a narrow range. So that's an extended driver gas concept we've used. Typically with tailoring, you can get up to about 10, 15 milliseconds. So you got to do things fast. Okay. Now I want to lead you through how people might have used this to study what's called vibrational relaxation. So we talked about the potential energy well of our simple harmonic oscillator. And if you were at T1, 300 degrees, all the molecules are down here in V equals 0. Now suddenly the temperature goes to 2,000 Kelvin. What happens? You begin to populate some of these upper vibrational levels. How does that happen? It happens by collisions. So let's just say that it's carbon monoxide. The carbon monoxide, in order to go from V equals 0 to 1, has to have a collision which has enough energy to bring it to level V equals 1. And so some fraction of the collisions will have enough energy. The fraction depends on the temperature. The higher the temperature, the higher the probability that any one of those collisions is going to have enough energy to make this happen. So it's a collision time dominated relaxation process. Here's the energy, potential energy 1/2 kx squared that we talked about. Here's the frequency in terms of the spring constant K, and so on. We went through that early on. These energy levels are quantized. Usually we call this level 0. And the question is, how long does it take to populate these states into a Boltzmann distribution? You can calculate, the process always goes towards equilibrium, but when you suddenly change the temperature, there's a new equilibrium. Equilibrium in which you have to provide some added population to these levels, according to the Boltzmann distribution. This is the Boltzmann distribution. So here's the fractional population in level I, minus I theta V. You know what theta V is? That's HC over K. That's a 1.44 times the frequency spacing in wave number units. If I know the wave number spacing for CO is 2100 wave numbers, that means that the characteristic temperature, theta, is that number times 1.44, so say 28,900 Kelvin. So you get a feel for this right away. If I produce a sample, a test gas at 2,900 Kelvin, I have to start having some population up here. How long does it take to get there? Well, that's the vibrational relaxation time. It's a question of how long does it take collisions when the gas is at, say, 3,000 degrees Kelvin to make this happen. That's what it's all about. Now, if you are, say, room temperature, 300 degrees, and I show the population as a function of the vibrational level I, at 300 degrees, essentially everything is in I equals 0. But if I go to high temperatures, there's some population in 1, 2, 3. And the higher the T, the more this thing spreads out. But by the way, as long as temperature is positive, there's always fewer molecules in the next level up. That's like the very definition of positive temperature. So that's an interesting point. But we can generate, in some methods, we can actually generate negative temperature by putting more population in a higher level than you should have. And that's the basis of a laser, extra population in an excited state. But gradually, in this case, we're going to just study the evolution of this distribution as it moves its way up. So you start here, and over time, this distribution evolves until it looks like it should at equilibrium. That process is called vibrational relaxation. The process is usually dominated by what's called VT, vibration translation energy. So the temperature, ultimately the kinetic temperature, T, has to equal the vibrational temperature, T sub V, of this Boltzmann distribution. Equilibrium, all the temperatures are the same. So in chemistry, we talk about reaction rate equations, but in vibration relaxation, they talk about a vibrational relaxation expression. So now we say the rate of change of the vibrational energy of this molecule depends upon the difference between its current value and its ultimate final value, that delta, divided by a characteristic time tau. That's called a relaxation equation. And that was derived by some famous physicists, Hans Bethe and Edward Teller, usually called the Teller relationship. The point being that we don't talk about the populations in specific levels. We talk about the evolution of the vibrational energy. And this characteristic time tau can be shown to be, from this equation here, was derived by Landau and Teller, two other, Landau, a Russian physicist, where Z is the collision frequency and M is the concentration. So this number taken together is essentially the collisions that a molecule experiences. And this is a fundamental probability of transitioning between 1 and 0. And this is our usual induced emission term. So as temperature goes up, this time goes down. And so let's see, I think my next plot might show. How can we measure tau? Okay, so let's imagine we do an experiment in which the temperature T is versus time. Here's the region 1. Here comes the instant shock wave. This shock wave gives us a step change in the translational temperature. That's the kinetic temperature associated with the random motion of the molecules. But now we have a vibrational temperature. That is the Boltzmann temperature that characterizes the vibrational energy distribution. It rises more slowly. So I can tell you that in the limit of a harmonic oscillator, there is always a vibrational temperature. It's just meaning there's always a Boltzmann distribution. but it may not be the translational temperature. It takes time, it takes collisions for that vibrational temperature, which was at 300, to evolve until it matches the translational temperature. So in the meantime, you're adding energy to vibrations, you must be cooling the gas. So the translational temperature goes down, the vibrational temperature goes up. Now the reflected shock comes by and you do it again faster. So eventually, all temperatures must match. The question is, how long does this take? Why do people care? Well, if you were operating a hypersonic facility and you had high enthalpies and you were expanding this flow in a nozzle to get high velocities to flow over some body, do some aerodynamic study, you might have to ask, well, what's the temperature of my gas stream? Now it gets a little more complicated. What's gamma? Okay, so it's not so easy. So you have to have some sense of how long these things take. And there was a lot of interest in this back around 1960s. So we would define the characteristic time based upon something like this. We'd extrapolate the initial slope, and we get this characteristic time that was in that beta-Teller theory. It's faster in region 5 because temperature in 5 is higher. So it takes a smaller number of collisions until you have one that brings about vibrational change. Back in that period of time, this was probably around 1960, 62, 63, pre-laser. People had to use other tricks to study this problem. So the theorists told those who were doing the science, the theorists said you should plot. The time is inverse with the pressure, so let's plot this as pressure time. Pressure time should scale with t to the minus 1/3. There's a reason for that. So in chemistry, we typically plot 1 over t down here for a rate constant, but in vibration relaxation, you plot t to the minus 1/3. So the experiments were done, and so in pure nitrogen, so for example, at 2,000 degrees, looks like it'd be about 10 to the minus 3 seconds if you're at 1 atmosphere. So it's about a millisecond at 1 atmosphere at 2,000 degrees. So the question is whether a millisecond is fast or slow for you. If, on the other hand, you do pure oxygen, now it's quite a bit faster. It's 2,000 degrees. It's probably that's probably about, I don't know, 8 microseconds or something like that. And if you have some sort of mixtures of nitrogen and air, it's going to be in between. You see a lot of scatter in these data. And you have to understand how hard these experiments were in those days. What people used was interferometry. They mostly measured what's called a Mach-Zehnder interferometer. So is there anybody in here who even knows what a Mach-Zehnder interferometer is? It's a device in which you pass the light through the gas sample, and you compare that path length with another path length. And so as the density is changing behind the wave, you're changing the wavelength difference of not the attenuation now. You're just changing the phase of the light relative to the controlled path. By measuring that phase change on what's called an interferometer, you could get a pattern like this. This is a case where the shock wave is moving to this way, and at an instant in time, here's the shock wave. This is the density, the fringes they're called, the fringes. And this is the fringe pattern that you have between the reference beam and the transmitted beam on this interferometer. This is called Mach-Zehnder. Just saying that, and that fringe spacing corresponds to some amount of density difference. Now behind the wave, what happens is you see these fringes are moving. They're moving this way as the density is changing. Why is the density changing? Because the temperature is changing. So as the temperature is changing, the density is changing, and you can see this shift in the apparent density. You can say, well, roughly speaking, I want to go 1 over E of the final change, and that's my characteristic time. That's how they were measured. Density-sensitive interferometry, not species-specific. So a lot of scatter, but you could get some feeling for this, and then the people who are doing aerodynamics facilities can decide how to evaluate the conditions in their tunnels. Now lasers come along. So I'm going to show you the power of using a laser technique. We have been studying vibration relaxation of oxygen, and it's motivated by Air Force interest in what happens as the vehicle enters the atmosphere or flies in the atmosphere very, very fast. So if it's flying very, very fast, there's a shock wave in front of it. The shock wave is taking that static air and converting it to higher temperature air. And if you want to compute the flow field about this body, you have to take into account the energy transfer between translation and vibration and even the chemistry. But right now we're just doing the vibration, like I say. So you need to have a model for the rate of change of vibrational temperature with flow field. So we actually want to measure oxygen because oxygen is an important constituent in I've told you that oxygen is homonuclear. So not only does it have a complication of nuclear spin that we haven't dealt with, it does not absorb infrared, but it does absorb in the ultraviolet for rho vibronic transitions. So our strategy is going to be heat O2 and argon initially, and we use a laser, we call it MIRA. It's a titanium sapphire laser. It allows us to produce light at any wavelength between 206 and 245 nanometers. So we calculate the spectrum of oxygen in that region, we pick a wavelength, and we can then, by changing wavelength, actually measure the population density in different vibrational levels. That's the trick. You really like that. Why? That's because it's not harmonic, it's anharmonic. So we can actually probe different vibrational levels by playing this trick. Now, this is not an easy trick. This is took us some years to do this. So here's Beer's law, our usual Beer's law. It says the fractional transmission goes to e to the minus the number density in the vibrational level we're probing times the cross section. So we have to spend a lot of time getting this number right here. We do the experiment, and we measure the alpha as a function of t, and we infer what we're after, namely the number density in a specific vibrational level. And is under the assumption that it's Boltzmann, we also then have the vibrational energy that goes into the Bethe-Teller equation. So we got some sort of a Ti-sapphire laser. It's a complicated laser, expensive laser, but we can tune this output to produce it essentially any wavelength we want. Gives us plenty of power, 2 to 20 milliwatts. It's a pulse laser, actually. It pulses at about 80 million pulses per second. So our detector is so slow, it only sees microseconds. It looks like a steady light bulb to my detector. So how does this relate to the vibrational population? So if you do the spectroscopy, and this is like a 12-month project for one of my students, you could calculate the strength of the lines as a function of the wavelength of the lines and see that the lines in the V double prime of 0 are on this curve. Now, this is the rotational distribution. I'm looking at the individual rotational lines in V equals 0, which are not exactly at the same place as the ones in V double prime of 1 or 2 or 3 or 4 because of the anharmonicity. So we know that if we work at about 206 nanometers here, it's mostly V double prime of 3. We do a lot of work at 211, it's mostly V double prime 4. So we are potentially able to probe different vibrational levels and test the hypothesis that there is a Boltzmann temperature. It just isn't the translational temperature. That's the idea. Here's a result. Here's a measure of absorbance versus time at a case where we had 15% oxygen and argon. So we mix up a known sample of gas, put it in a shock tube, heat it to a known temperature of 1272 Kelvin. And we're measuring now the absorbance in V double prime of 4. It's initially 0. Now, it takes a little bit of time, but gradually it builds up. There's kind of a induction time here. Why? Because there's nothing in V. The favored transitions are still delta V of 1. So 0 has to go to 1, 1 has to go to 2, 2 has to go to 3. It takes a little while to begin to build up 4. When we do this, we fit it, we find good agreement with our simulations, which are based upon the characteristic time in that energy equation. And we can then plot this on a diagram like this. Here's our data points versus t to the minus 1/3, pressure time. The good news, there's good news and bad news. So Millikan and White, back around 1960, so 63, used their interferometry schemes and were able to do O2 and argon and pure O2. And the lines, the dashed line was theirs. Extrapolation of their data. The circles are, squares are our data. So the good news is we have really nice low scatter, very much better data than other people have. So the good news, bad news is that, but it's no different than, so even we went through all this work only to find out that those guys were pretty good. They did a good job. And it's pretty close. So the ability of the laser is to give low scatter, high quality data. But in fact, it hasn't changed knowledge. It hasn't changed what the world thought these relaxation times were. We're still working on this. We're trying to push up to 1,000 degrees Kelvin. I want to move to chemistry now. So you want to look at the chemistry of hydrocarbons, and where, if you've had, probably everybody in here, or 3/4 of you at least, have had courses in which you talk about the chemistry of ignition. And you usually start by talking about hydrogen and oxygen. So you have hydrogen and oxygen, and you suddenly raise the temperature. But it's 300 degrees, it's safe until you light a match. Now, what if you raise it to 1,500 Kelvin? What happens? You can calculate equilibrium using chemical equilibrium arguments, but you can't calculate how long it takes. That is a chemical kinetics problem. So you'd like to study, and that's based upon the idea that these reactions proceed, that there are many reactions that can take place. So for example, it's thought that, well, initially you have only hydrogen and oxygen, so the only thing that can happen is the binary collision between these two molecules, probably producing this thing called hydroperoxyl plus H. And then once you have an H, you can have the H plus O2, one radical produces two, that's called branching reaction. And then that produced O reacts with hydrogen and you get two more. So those are so-called branching reactions. And this H and the OHs that are produced can react also. So there's like 3 ways that you can get an increase in the number of radicals. Once you form one, these things take place and you rapidly grow the pool of radicals. That's called ignition. You can lose radicals by recombination reactions or by walls. So this is the way usually combustion professors will tell you about the chemistry of hydrogen-oxygen ignition. And each of these reactions is thought to be a real reaction, that hydrogen and oxygen come together. Oops, I'm going to go back here. It actually is a representation of reality. Swept under the rug are all sorts of questions. Well, don't we have to think about this in specific quantum states? There's a lot of stuff swept under the rug on the idea that if you know temperature, you can properly, that's enough to average out the influences of all these details. So the current state of the art is to say that this is a reaction with a rate constant K that depends upon temperature, and we don't have to get into the nitty-gritty of quantum states. The theorists would say you have to do more of that. So the net effect of these 3 reactions is that there's this step here, this step here. This is the important one. This H that's produced here goes to 2 radicals. And this is an endothermic reaction that requires about 17 kilocalories. The other steps here are essentially energy neutral, so they're fast. So as soon as this happens, you more or less quickly have the other steps. So effectively, if you add these things up, that H reaction, this H is converted to 3H. So the delta is 2. That every time you get one of these, you get 2 extra ones. So that is explosion. That radical pool, you know, as soon as you have, if you take that number of times that, fraction of times that it happens, it quickly explodes, and that's called ignition. Of course, these reactions also generate heat release and pressure increase in a real device. So what is a real device? Well, you might do this in a bomb, you might do it in the atmosphere, but we would do it in a shock tube. So we would do this now in a shock tube. Here's our pressure on this side here, and here's the emission that we might observe from our sample. So we do an experiment where here's the incident shock wave, here's the reflected shock wave, so we call that time 0. So at what we'll call time 0, the pressure jumps to 3 atmospheres and 1124 Kelvin. The question is, how long does it take to ignite under those conditions? So for this gas mixture, we see a rapid change in pressure at about 180 microseconds. So we've just determined the ignition delay time at this condition. So we use step heating, and we wait until it ignites. We call that the ignition delay. That's the crudest measure of ignition delay time. You could do this in other devices, but I think it's best done. People do it in a rapid compression machine. That's our competition. I would say that we're better because we can control the temperature and make it more uniform than them. But the rapid compression machine allows access to longer test times. We typically would use either emission of light or the change in pressure and extrapolate it back to zero and call that the ignition delay time. So that's how you could measure ignition delay time. Then the people who do kinetic modeling would build their reaction models and tune the reaction rate coefficients until they match this observation. That's basically how it's been done for a long time. And gradually over time, some of those reaction rates are known better and better, and so you don't change those anymore. But it all rests on experimental data of this type. Typically, you use pressure and emission of light. What OH star means emission from an excited electronic state. Oh, 306 is the same thing we've been studying, only now it's emission. And so you repeat the experiments, you see how good they are, and that's kind of how it's done. Well, if you progress now to look at a more complicated fuel, let's look at, say, the so-called normal alkanes. That would be methane, for example, is methane. And if you look at this would be butane and all the way up to, say, nonane. So if you vary the carbon number in this particular hydrocarbon paraffin fuel, fixed oxygen, at equivalence ratio of 1 and fixed pressure, how does the ignition delay time depend on temperature? What you'd find is that the bigger the molecule, the faster it ignites because there's more CH bonds available to interact. So this kind of makes sense that the larger the molecule of the given type, the shorter the time. But it's not very dramatic. And for a long time, people just said it was a fixed number. So you'd use data of this type for the theorists to build their chemical kinetics mechanisms. This is now 1250 high and higher. What if you go lower? If you go lower, you have this interesting observation that the ignition delay time starts becoming independent of temperature, and then it goes up again. So that's telling the theorists that the chemical kinetics mechanism is different. It's different here than it is in this region. We call this the NTC, negative temperature coefficient regime. Negative temperature means that for some reason you go lower in temperature, the ignition delay time actually gets shorter, kind of as counterintuitive. But that's because of the details of the chemistry. This effect is larger in these normal alkanes than in other gases. Then it goes up again. So clearly, the chemical mechanism that's happening here is different than the one that's here, and it's different than the one that's here. So that's the virtue of these experiments, to help the theorists figure out what is the right chemical picture. So you need experiments to guide the theory. So over the time, I've been doing this a long time, and we gradually want to make, I want to make shock tubes better and better and better. I say I want to make shock tubes great again, but that's my political leaning. So the idea is, well, how do we get more test time? Because I want to beat out these people that run our rapid compression machines. How do we? Because I think we're better. Because we have more uniform flow, we don't have the crevice problems and so on. But we need more test time, and we need to learn how to do that well. And it's also true that when we look at our post-shock pressures, they should be constant, and they're not. And so we found a way to fix that problem. And we got some new approaches. So anyway, this is a set of the things that we've tried to do to make our shock tubes better. Here's another picture of our shock tubes. This is one of the tricks that we use here. We extend the driver with a loop and make it longer. And it's kind of a typical optical setup. And so this is the reflected shock end of this tube. So they're typically 40 feet long, say, diameters. Bigger is better. Bigger diameter is better. They tend to be 4 to 6 inches in our laboratory. Because most people have a fixed length of room, I decided, well, we can't change the room, but I'll change my driver. Just make it longer. That works. Other people are doing this now. So the first thing we'd like to do is extend the test time. So if you have our here's test time here in milliseconds versus temperature. Here's temperature. This is roughly the box in which we were working with our shock tubes. We get a few milliseconds over a wide temperature range. This is the curve we would calculate for endodecane, that's C12H26 in air at, I think, about 10 atmospheres. So it looks like, gee, we can't quite get to that NTC region. So what are we going to do? We're going to have to get, the RCM people, they're kind of mostly up here. They can't really get below 10 milliseconds because they have all this problem with the fact that they're compressing it. They can't get a step change. We both have a problem. So we're going to change our shock tube so that we can overlap. Or we'll play some tricks to do this. So basically, the first step is you increase the length of the driver by 2. That means you delay the time it takes. So you assume it's tailored. You delay the time of the rarefaction wave arrives. Then we play some more tricks. So we can get some pretty long times, up to about 100 milliseconds. That should give us access to studying this very intriguing region right here. And also, it's beneficial to test chemistry under different, so it's good to do experiments in 2 types of machines to see if you get the same answer. Usually you find that you don't. And then when you finally figure that out, you realize that there's ways you can make your facilities better. So it's very good to compare between different laboratories and between different facility types. Here's a problem. How am I doing on time? Okay, here's a problem. Here's the pressure in red versus time for a propane-oxygen mixture. I think that's equivalence ratio 0.5. So you have 1,000 degrees. You do an experiment, and we use a lot of argon because that makes the experiment better. Ideally, you would have constant pressure. But in the laboratory, you find that it actually does something like this. Even when we tailor, so this little bump right here is because we've gone from a test time of about 3 to about 10 by tailoring, but the tailoring equation assumes that you have a planar interface between the driver and the driven gas, and it isn't, it's a zone. So for those reasons, you never really can get this perfect. But basically, this is what we get when we do tailored operation. We can get to 11 milliseconds, but what's this thing going on here? I call that, and now it's other people call it, the dPdT effect. That is the influence of the attenuation of the instant shock wave due to friction on the sidewalls, causes the post-shock pressure to rise. And if pressure is rising, the temperature is rising. So even if you assume it's isentropic, and if you assume that the gamma is 5/3, the temperature change is 40% of the pressure change. So if I have 3% per millisecond over 10 milliseconds, meaning 30% change in pressure, I've got a 12% change in temperature, and that's a killer for chemistry. You just cannot have significant temperature change in an experiment, or you're going to have a lot of error. So that's the idea. We're going to fix this problem. We're going to recognize the source of it, and we're going to get away from the concept of using a fixed area driver. We're going to have a variable area driver by using what's called an insert. And we designed this insert so that the expansion waves that go this way then come back and they weaken the shock wave so that we can achieve more constant pressures. And this is how well it works. Of course, I'm showing you the good results. Here's the blue one. Now, all of a sudden, we've got the pressure. We still got this little tailoring problem, not a big deal. But look how much more constant this blue is than the red. Much better experiment. Much better experiment. And look what happened. The ignition delay time, instead of being this number, is now this number. So if you were modeling this experiment, assuming constant conditions, you better use these data, not these data. These data represent a variable temperature environment. So there's a lot of issues about this, how to do it better and better, but it's all about controlling temperature and pressure in your reactor, because temperature is so important in chemistry. So this is a big improvement. And so what did that mean? This was really a big deal because people were plotting their ignition delay times here, milliseconds for propane. Here's some results that were taken in Wales by a small diameter shock tube with a large attenuation rate and therefore a big dPdT. Cadman was his name. Here's the results that we were getting in our shock tube before we made the driver change. Here's the results that we get after the driver change. So if you're at really high temperatures, it didn't make any difference. But when you get to longer times, more than a few milliseconds, so this is our improved shock tube, this was our original shock tube. We modeled this with something called ChemShock, which was a code that just says, if you tell me dPdT, I can correct for this problem. So I could model these data knowing that dP/dt was 1.5% per millisecond. And I can even model his data, recognizing he had a really big 12% change in pressure with So basically, all of this is about controlling the reaction environment and making it better and better. So you need to do this in order to get better quality data. So and the people were modeling these experiments as if they were ideal. Well, if you're going to match this, then what happened is they had an incorrect chemical kinetic model in order to match the data. So the modelers tend to think the experiments are correct. Experimentalists know they're not perfect, but we can make them better. So the first clue was we were getting much different data than Cadman. And we realized what's going on, and we tried to fix the problem. So that's the state of the art for shock tube studies. Nowadays, the good papers in the literature report their dP/dt so the modelers can take it into account. For example, using something like. So now here's a problem. Here's another problem. Most people assume that the reflected shock reactor is constant volume, but it's not constant volume. It's got solid walls, it's got a solid end wall, but the other boundary is a moving shock wave. It was not a constant volume problem. It may be nearly constant volume, but it's not a constant volume problem. So it's not constant volume. So look what happens with heptane ignition. Here's heptane case 1380, and here's our ignition right here. That's the so-called sidewall pressure that we measure. So a constant volume model would predict bigger pressure change. It's clearly not constant pressure. It's not constant volume. What is it? In model chemistry, you've got to have a thermodynamic constraint. You have to specify the conditions of this gas. Usually you assume it's adiabatic, and then the modelers would say constant volume, but it's not constant volume. And it's not constant pressure. This is what you would calculate if you said it was constant volume. We're in between. So you're okay for a while, but then what? So if you want to model throughout this process, and you want to model more accurately, we got to deal with this problem. That's kind of the state of the art. Some people are now kind of coming to grips with this. We decided, I tried for a while to make it into a constant volume, I couldn't do it, but I figured out a way to make this close to constant pressure. So the idea was minimize the amount of fuel. So the amount of energy released is small, and therefore the change in temperature and pressure is small. That's pretty obvious. So you could do that, or you could use what I call my constrained reaction volume idea. In this constrained reaction volume idea, this is what you usually do. You fill this chamber with the test mixture. And then you have this region here that's releasing energy because it's exothermic, and you get, therefore, large delta P and delta T. What if you do it differently? What if you just fill this little section right here with test gas? Now the test gas is compressed to this region here. The amount of energy released is smaller. Maybe we can control the pressure change. And sure enough, over some wide range, it works pretty well. And when you do this, by the way, that means that some other non-ideal effects that sometimes cause the ignition to occur out here and propagate in are defeated. So there's some benefits to this scheme. Of course, it's not easy necessarily to do in the laboratory. So this is the conventional shock tube, normal filling, and you'll see this big pressure change. Now, if we repeat that experiment with the constrained reaction volume idea, instead of getting this pressure jump right here, it's combusting. We see the emission, but the pressure is not changing. Why? Because the diameter is big enough that it's relieving itself axially. This is starting to burn. As long as it's burning halfway slowly, the pressure can stay nearly constant. So it's not a perfect answer, but it's a way to allow better experiments and therefore better modeling and better knowledge of the chemistry. But this is the first, to my knowledge, the first time you could do kinetics modeling throughout the entire, you can just keep modeling. Now, the pressure is not exactly constant, so I would impose what's called the specified pressure model in ChemKin. This is just some examples that show if we looked at ethylene experiments. If we do the, first we do a non-reactive experiment without ignition, that's the blue. We measure now with the constrained reaction volume in place. You can barely see the ignition takes place. So now, of course, you can't use pressure to indicate ignition anymore. You have to use something else. So we use temperature. Oops. So we have a way of measuring temperature. We'll measure temperature throughout this cycle. And here's what you get with what's called JRIMEC, and here's the jets, different chemical kinetics models. So for the first time, we have the ability to model through the ignition process by converting their shock tube into a constant pressure reactor. I think this is promising. This is kind of the state of the art. So we've now looked at some other fuels like butanol, and you can see these were the data. These were the data we got before we fixed our shock tube. So if the modelers assumed constant volume and tried to match this data, they would have to adjust their rate constants away from the ones that are really correct. So a better quality data leads to a better mechanism. All right. And so at high temperatures, it turns out this is really short times. Times less than a millisecond, this is not a problem. At low temperatures, longer times, this is a significant experimental error. And you can draw inferences that these same effects are present in RCMs. You just have to really think carefully about how your device functions. So I think these are improved reaction rate data made possible by modifications. So, advancing your science is usually a bootstrap thing. The theory gets better, you do a better experiment, they adjust the theory. The experiment and theory help each other get better and better. So you look for discrepancies between experiment and theory, and then you use that to try to improve your design of your experiment. So again, this is just another example of one butanol in air, 20 atmospheres, between old design and new design. Okay, and so the ignition delay times are longer, and so the models are incorrect if they try to replicate this without taking these effects into account. Okay, so I finished this. This was your introduction to shock tubes as a way to study chemistry and spectroscopy, and the aerodynamics people would have a nozzle on the end of the shock tube. They compress the gas, have another little diaphragm, and they expand that high enthalpy gas in a nozzle and study aerodynamics over a body. So it's a way to produce high enthalpy gases for use of chemistry, physics, heating, aerodynamics, and so on, heat transfer. So in the next hour, I'm going to try to go heavier into the chemistry side, talking about how we use lasers to study individual chemical reactions. Yep.
You said earlier that
Yes.
what is that?
Okay, so argon has a gamma 5/3, whereas say nitrogen has a gamma of 7/5. And it turns out that a problem that I haven't told you about is called bifurcation. So when the incident shock propagates along, comes to the end wall and comes back, that reflected shock has to do something on the boundary layer side. And so there's some funny business that goes on in the interaction of the reflected shock wave and the sidewall boundary layer. And when the gamma is 7/5, this region gets heavily distorted. When it's 5/3, by chance, it's practically mitigated. So you should get better experiments if you use argon. On the other hand, a lot of people, the engine people, don't want you to use argon. They want you to use air. So we go back and forth trying to compare and make sure we understand things. But yeah, one of the problems of a small shock tube is that this bifurcation region can become a significant part of the diameter, and you don't want that. You want to be able to neglect it. So argon solves that problem over some Mach number range. Any other questions? Okay, so we'll resume at 11:15.